Hello everyone, welcome to Recitation of CEE222 Water Resources Engineering. This is week 7. This week we will have 3 different questions and it will be very short actually, and we will get started with 6.2.1. So first let me read the question. Here we have a concrete channel with an unusual cross section, as you can see, and it carries a water at flow rate of 30 cubic meters per second, and we need to determine the channel slope. So first of all, since we have a flow rate, we can calculate the velocity, or we can directly use Manning's equation, which includes slope, area, Manning factor, and everything. So that let me get started by writing the Manning's equation. According to Manning's Q is equal to 1 over n, which is Manning's n factor, plus hydraulic diameter, sorry, it's not plus, times hydraulic diameter times channel slope times area. So we wrote this equation because we are dealing with an open channel, and Manning's is very important for this type of channels, this type of flows. So that we wrote the Manning's equation, and here, since we are asked to find slope, and since we know the flow rate, we know Manning's n factor, we know diameter, we know area, we can directly calculate slope. So according to table 6.2, you will find that the Manning's n value is 0.013 for concrete channels. So here we have Q, which is 30, is equal 1 over 0.013 times hydraulic diameter, which is area over perimeter. We don't know the slope, and we have area. So to calculate the total area, we can do something like, we can create subsections. For example, let's say we have this section, we have this section, so that we have 1, 2, and 3 different sections to calculate the area. This is what I'm doing. So actually you can either use tables, or you can do something different, but the main point is calculating the total area of this flow, of this channel. So we have 3.6 times 2 for the area 1. Plus for area 2 we have 1.6, and the length will be 2 meters, and we have 1.6 times 2. And for the third one, we can calculate it as, again, we will have 2 meters here, and since we have 1.6 meters, the remaining will be 2 meters again. So the area will be 2 times 2 over 2. And from here we can get 12.4 square meter, and for the perimeter So we can start from this side. We have 3.6. We have 2. We have 2 root square 2. And finally we have 1.6. Actually, you cannot see that. So we have 1.6 and this is equal to 10 meters. So here we actually have everything we need. So we already know the flow rate, we have Manning's n value, we have hydraulic diameter, which is A over P, which is 12.4 over 10, times the only unknown is the slope, channel slope, in a root square, and finally we have area. And if you use your calculators, you will get channel slope as 0.000742. Okay, question 2. The new question is 6.2.4. And let me get started with the question text. So, here we have a 3 meter wide rectangular irrigation channel, and it carries a discharge of 50 cubic meter per second. The channel slope is 0.041 and the Manning's coefficient is 0.022. We need to determine the normal depth using successive substitution. So first of all, let me talk about the successive substitution. And in your textbook, if you check figure 6.2, you will see 2 graphs, and for example, it will be something like that. So on the x-axis, we will have NQ over Km, channel slope, and channel width. And on the y-axis, we will have normal depth over the width of the channel. So this is actually for trapezoidal channels. And in the table, you will see that we will have m values as like 1, 2, 3, 4, and it refers to side slope. But if we have a rectangle channel, we will have curve like this. So you will see the details in your textbook. Then you can find the intersection of these 2 axes and you can get the normal depth. So to find that, we should get started. So first of all, we need the area of this rectangular channel. And the area is, we have 3 and we have normal depth. So we have 3 times yn. And for the perimeter, we will have 3 here and 2 normal depths. So 3.2 yn. Again, since this is an open channel, we can use the Manning's equation. So it will be equal to Q is equal to 1 over 0.22 plus hydraulic diameter, which is 3yn over hydraulic perimeter, which is 3 plus 2 plus 2 normal depth over 2 over 3. Then we will have the channel slope times area. And we can actually write this because it was already given. So here we have 50 cms, 50 cubic meter per second flow rate. And we can use two calculations. The first one is direct calculation. So if you use your calculators, since we only have normal depth as unknown, and we have other values. This is also 3yn. Since this is the only unknown, the normal depth is unknown, we can use our calculators and we will get 2 meters from here. And in the question, we also asked to find the normal depth using successive substitution, which is this figure, this table, this graph. So let me go with it. So for the x-axis, we have 0.022. We have flow rate 50 over. This is usually 1. If you will have different values, it will be given in the question. So we have 0.1, 0.041 times the width, power of 8 over 3. So this actually gives 0.29. And on this side, this time we will have normal depth over B, and B was 3. So when we use this table, for example, let's say we have 0.29, and since we have this rectangular curve, we will intersect this curve with our x-axis. Then we will get the value on the y-axis. So if you check the figures, you will get something like 0.63. So this means that normal depth over B is equal to 0.63. So yn is 0.63 times 3, which gives 1.89 meters, and which is actually very close to this value. So basically you will have two different approaches to calculate this normal depth. Let's continue with question 3. This is 6.2.8 question. Okay, in this question we have a uniform flow, and it occurs in 20 feet wide rectangular channel, as you can see here, with a discharge of 2520 cubic feet per second, and we have normal depth as 15 feet in this first channel. So the question says, what will be the new normal depth in this second channel when the width of the channel expands to 30 feet? So here we had 20 feet wide and 15 feet normal depth, and the question says, what happens if we expand this width of the channel as 30 feet? What will be the new normal depth? And we will assume that the slope and channel roughness remain constant in both channels. So we know that the flow rate will be same for both of these channels. So we can write Q1 is equal to Q2. This will help us to equalize both of these channels using Manning's equation, because in the Manning equation we will see the impact of this expansion, so that we can eliminate some values and we can get the normal depth for this channel. So since the Manning's equation is written like this, this is hydraulic diameter, slope, and area. And as the question says, we can assume these values as constant, so that we don't need to actually find the Manning's N coefficient, and also we don't need to find the channel slope, because they are constant in both of these channels, so that we can ignore them. However, we need to find the area and area and perimeter for these channels. And let's say A1 is equal to 20 times 15 feet, which gives 300 square feet. P1 is equal to, we have 20 and we have 15. Even though we don't know the normal depth, we can still write the equation. We can still write the area and perimeter for this channel. So A2 is 30 feet times normal depth, and the perimeter is 30 plus 2yn. So since we said these two flow rates will be equal to each other, like Q1 is equal to Q2, and since we have the same Manning's equation for both of these channels, we can actually write this equation. So let me write it like, since we are using British, we will need to change this actually. So it is 1.49 over n. We have 350. We have slope, and we have 300 area. This is equal to flow rate in the second channel. So similarly, we have 1.49. We will have hydraulic diameter, hydraulic radius, and we have 40 yn over 30 plus 2yn. And we have channel slope, and we have area, which is 30 yn. Since the question said that the Manning's value and slopes are constant, we can directly eliminate this. And the remaining equation is, we only have values here, like hydraulic radius times area equal to, again, hydraulic radius times area. And since the normal depth is the only unknown here, we can directly use a calculator or any software. So we can get the value as 10 feet.